Hello physicists and welcome. In this session we'll be looking at rotational kinematics. Hey, let's establish our variables. We'll start with the variables that we're used to in the linear variable world. And we'll take a look at what their correlation or their analogy is in the rotational world. Hey, for position we've been using the value x. In the rotational world we'll use the angular position theta. In the linear world, we've been using the letter v for velocity, which we can also look as the derivative of position with respect to time. And in the rotational world, we'll use the small letter omega. And we can also look at our instantaneous velocity as the derivative of our position function with respect to time. Again, we've been using the letter a for acceleration, which was dv dt. And in the rotational world, we'll call that alpha, which is going to be d omega dt. A time in both worlds, both in the linear and the rotational world, is represented by the letter t. To translate between each of these systems, we can look at our linear position is really just the radius of our rotational world times whatever the variable is. Position is equal to our radius times our angular position. Velocity is our radius times our angular velocity. And tangential acceleration is equal to our radius times our angular acceleration. Hey, if there are analogies in our variables, there have to be analogies in our equations as well. Hey, so let's go quickly through these. Hey, the linear equation. Hey, if I'm looking for my change of position, I can look at it this way. If I know my acceleration and my time and my initial velocity, 1/2 at squared plus my initial velocity times time. The correlation to that in the rotational world is the change in my angular position is 1/2 times my angular acceleration times time squared plus the angular velocity times time. Hey, how about our average velocity? Hey, our average velocity is just our change in position over time in the linear world. The correlation in the rotational world is our angular velocity is the change in angular position divided by the time. Hey, again for acceleration. Our acceleration is the change in our velocity divided by time. And in the rotational world, we'll look at our angular acceleration is equal to the change in our angular velocity divided by time. And then we'll go to our favorite kinematic equation. We know that our final velocity squared is equal to our initial velocity squared plus 2 times the acceleration times our displacement or our change in position. And yes, that also fits in the rotational world, that our final angular velocity squared is equal to our initial angular velocity squared plus 2 times our angular acceleration times our change in our angular position. Let's try an example problem. And we have a wheel starts at theta equals 2 radians and rotates at a constant 3 radians per second. What is the rotational displacement and angular position after 12 seconds? Hey, let's go establish a couple things here. So we're looking at the rotational world, so we'll look at rotation of about a disk. We're going to call this position the 0 position, and that way, so I guess if we view it counterclockwise, is going to be our positive rotation direction. Okay. Hey, so let's go ahead and get started at this. Okay. I want to know what do I want to look at here? What is my rotational displacement and my angular position after 12 seconds? Okay, so one of the things I'm looking at is my rotational displacement and then my final angular position after 12 seconds. Hey, what am I given? Hey, I'm given my initial position is 2 radians. And I think by now you know a complete rotation around this circle would be 2 pi radians. What else do I know? I know my omega is equal to 3 radians per second, and my time is 12 seconds. Let's look at our relationships. Hey, all the linear relationships also apply in the rotational world. So we'll say that our change in angular position is really equal to our rate of change, which we call our angular velocity times time. That's going to be pretty straightforward. Hey, I'm rotating at a rate of 3 radians per second for 12 seconds. And 12 times 3, okay, what is that? 36 radians. My change in position is 36 radians. And we want to know our final position. Hey, my final angular position is equal to my initial angular position plus my change in angular position. Let's go and put in some numbers. I started off at 2 radians. I changed 36 radians. My final position, 38 radians, is my final angular position. Let's go and bracket both of these. Hey, let's take a look at another problem. Hey, we have a wheel starts from rest at an initial angular position of 5 radians. 8 seconds later, the wheel speeds up uniformly and is rotating at 32 radians per second. Calculate the angular acceleration alpha and the final angular position for the wheel. And let's draw a little picture here. Hey, so 5 radians. We know that there's 2 pi, or a little over 6 radians in a circle. So if I'm calling this 0 and this is the positive direction, both for angular velocity and for measuring our angle, that we're starting somewhere around here, I guess. Okay, as our initial position at about 5 radians. Okay, it's starting from rest and then speeding up in this direction because we have a positive, acceleration. We have a rotation of 32 radians per second starting from rest. So I'm pretty sure the acceleration is going to be positive. So what are we trying to find? Yeah, I'm trying to find angular acceleration, and I'm trying to find final angular position. Hey, let's see what we can do here. All right. Hey, so I'm given, what am I given? I'm given time, and I'm given an initial. Okay, let's see. I'll go with my givens here. What am I given? I'm given an initial position equal to 5 radians. Hey, radians you probably know is unitless, but I'll put radians just so we know we're talking about radians. We have an initial velocity equal to 0. We have a final velocity equal to 32 radians per second. And what else do we have? We have t equal to 8 seconds. All right. Hey, so let's see what our relationships are. My relationship. Hey, I'm looking for alpha. Hey, I know that alpha is equal to my change in omega over my change in time, at least for the average value. Anything else? I want my final angular position. Oh, hey, it looks like I'm going to know time. I'm going to know my acceleration. I'm going to know my initial position. I can probably figure out my final angular position. Hey, and just a slight change of that one formula we have, I can say that my final, I'll call that final position is equal to 1/2 alpha t squared plus omega initial times t. Hey, let's go ahead and solve this thing. Let's solve initially for alpha. Well, it's going to be pretty straightforward. My change in omega is going to be 32 radians per second. I'm starting from rest, so minus 0 radians per second, and divided by the amount of time, 8 seconds. 32 divided by 8 gives me, I hope I have this right, 4 radians per second squared. Notice those units look kind of familiar. Similar to our linear acceleration, instead of meters per second squared, we have radians per second squared. Hey, so let's go and take a look at my final position. All right. Hey, I did notice a little error I had over here. Let me just adjust that. I'm going to erase this over here. Hey, my final position, let me go back here. My final position is 1/2 alpha time squared plus my initial angular velocity times time plus my initial position. Sorry about that error. All right, let's go ahead and we'll put numbers in. We can see if we can solve that. Hey, so my final angular position is 1/2 my acceleration 4 radians per second squared, my time 12, right? Oh, no, it's 8 seconds. Man, sorry about the mistakes. Erase. Eight seconds squared plus my initial velocity 0, don't have to worry about that, times time, and then plus my initial position 5 radians. Go ahead and we'll add this all up together. Okay, so I have 8 squared, 64 times 1/2, that's 32 times 4. Hope I get 128 radians here, plus my initial 5 radians. Tells me my final position is 133 radians. And we know every time we go 2 pi radians, we've got a complete circle. So what's this, about maybe about 20 complete revolutions, something around there. Hey, let's take a look at one more practice problem here. Hey, a wheel initially rotating at 20 revolutions per second speeds up to 60 revolutions per second while rotating 100 times. Calculate the angular acceleration and the time required. Hey, notice this time the values here are not in radians, but they are in revolutions. All right, so I'll have to do a little bit of conversion there. Hey, just kind of a little bit of a quick drawing here. So we know that it's moving in a positive direction, and sometime later on it's moving in a greater positive rotation. Hey, so what are we trying to find here? I'm trying to find alpha and time. Hey, what am I given? Hey, it looks like I'm given an initial velocity or initial angular velocity of 20 revolutions per second. I'm given a final angular velocity of 60 revolutions per second. And what am I given? I'm given, oh, okay. Hey, the change in position of being 100 revolutions. I'm suspecting I'm going to have to change these into radians eventually, right? Hey, what type of a relationship do I have? Oh, look at this. I don't have a time, but I have an initial and a final velocity, and I've got a distance. So looks like we can use our favorite kinematic equation to figure out some of this stuff, and we'll come back and figure out time. Okay, so let's go with that. My final angular velocity squared is equal to my initial angular velocity plus 2 times alpha times my change in position. Hey, so I know this, I know this, I know, so let me underline this. I know that, I know that, I know that, or at least can figure it out, and I'm looking for this thing here. Hey, so we're in pretty good position. Hey, and the other relationship that we have is that 1 revolution is equal to 2 pi radians. Hey, I am also being asked for time here, and so let's see, once we have that alpha, hey, I know that alpha is going to be equal to my change in, whoops, hold on that. Yep. My change in angular velocity over my change in time, which means we can rearrange this and figure out what our time is. Let's go ahead and solve this problem. Okay, so we'll solve. Hey, first let's go and make a note of what our angular velocities are. Okay. Hey, 20, let's see, we're at 20 revolutions per second. 20 revolutions per second times 2 pi tells us that our initial angular velocity is 40 pi radians per second. Our final angular velocity is, what we got, 60 revolutions per second times 2 pi will tell us that our final angular velocity is, what's that, 100, whoops, do I have that right? Whoops. Yep, 120 pi radians per second. And what's this last one? Hey, our change in position initially is 100 revolutions. We'll multiply that by 2 pi, and we find that we're going through 200 pi radians. Hey, so let's go ahead and solve that. Okay, so we'll end up saying, hey, what is it? 120 pi radians per second squared is equal to our initial angular velocity, 40 pi squared plus 2 times alpha times, sorry, I'm a little crowded here, 200 pi. Yeah, I'm going to kind of do a little bit of house cleaning here, all right? Hey, so welcome back. Just clean that up a little bit, and then I'll write the solution in blue just to provide a little more contrast. All right, so we have this one. We're going to have, what is this, 14,400 pi squared is going to be equal to 1,600 pi squared plus 400 pi alpha. Let's do a little cleaning up here. All right, if I take, let's see, 14,400 pi squareds and I subtract 1,600 pi squares, I end up with what? 12,800 pi squareds are equal to 400 pi alpha. We're trying to get alpha all by itself. So let's go ahead and we'll divide each side by 400, at least if my math is right. I hope it is. All right, so dividing that, 400 pi. Okay, let's see. Now we'll do a little fancy math here. All right, 12,800 divided by 40, what do I got? Oh, looks like I got 32. 32 pi is equal to alpha. So 32 radians, and maybe I'm going to clean that up just again a little bit too. So pausing for just a moment. Okay, so I've cleaned that up. So I get 32 pi radians per second squared is equal to our alpha, right? So our angular acceleration, so we've taken care of this one. Hey, how about our time? Hey, I see my relationship over here. I could rewrite that as, hey, my change in time is equal to my, let's see, change in angular velocity over my acceleration. Let's go put some numbers in there. So in this case, hey, I started off, and let's see, radian-wise, I started off at 20, I went to 6, whoops, let's go with this. I started off 40 pi and went to 120 pi radians per second, so we'll subtract that, and then we know what our acceleration is here. So what, 120 pi minus 40 pi, so what do I have? That's 80 pi radians per second. And I'll divide that change in angular velocity, the 80 radians per second, I'll divide that by our acceleration, 32 pi radians per second squared. Hey, my pi's cancel. 80 divided by 32 is like, what is that, 2.5? 2.5. I have seconds to, let's see, 1 over seconds divided by 1 over seconds squared. Get rid of all that, and I get 2.5 seconds. So how long does that take to speed up? 2.5 seconds. So it's very much like our linear kinematic problems. Should we just end up speaking Greek now? All right. Hey, so for now, that's physics.